In lecture 15 of the course Symmetries, Particles and Fields, we're going to work towards developing the algebra and this inner product space towards proving that the inner product space is actually, in terms of the roots, is actually a Euclidean space, which means that we can use results familiar to us from Euclidean geometry. So we're working towards the real geometry of the roots. If you remember last time, we defined these root strings. So the alpha string passing through the root beta is this set of various roots within the root set of beta plus some integer multiple of alpha. So if we consider now what the commutator of H alpha is with this root, which is beta plus rho alpha. Okay, so now we use our the Lie algebra that we wrote down in our normalized basis. So from 6.5, I think I called it. This comes out to be twice times the inner product between alpha and element of the root string. Times E beta plus rho alpha. So this I'll call equation 6.6. Okay, so from properties of the inner product, this right-hand side is just twice inner product between alpha and beta over the length of alpha squared, or the inner product of alpha with itself, plus 2 rho. All times is E beta plus rho alpha. Okay, so that's one of the commutators that we have, but we want to know what happens when we act on an element of this root string with either E plus or minus alpha. So if we look at 6.5, go up and look, we can see that when we have the commutator of two of these E's, it depends actually if the result is in the root string or not. We get 0 if it's not, and if it's in the root string. Sorry, if it's in the root set, then we get something proportional to the E represented by that element of the root set. So this is proportional to E beta plus rho plus or minus 1 alpha if beta plus rho plus or minus 1 alpha is in the root set, and it's equal to 0 otherwise. And if beta is 0, well, we don't consider the, so there is this other case of in 6.5, which is when beta equal to minus alpha, but we're not considering that case from the point of view of the root string. Beta has to be a non-zero root. Okay, so we define this vector space at the end of last time, V alpha beta. Now this is invariant. This space is invariant under this SL2 alpha. Okay, and so this can be viewed as a representation space for some representation of SL2 alpha, therefore. So some representation R of SL2 alpha, or this Lie algebra of SU2, the complexified SU2. So 6.6, our equation 6.6 here, this implies that something about the weights of this representation. So let's call this weight some set SR. And of course, the weights are really given by the eigenvalues of this H alpha operator. So R has weights SR, and we just basically set them equal to this eigenvalue here. So 2 alpha comma beta over alpha alpha plus 2 rho, where beta plus rho alpha is in the root set. So this equation here between E plus or minus alpha and the other E, this I'm going to call 6.7. So 6.7 implies that each of these weights has multiplicity 1. So we know that from properties of representations of SL, of SU, Lie algebra of SU2, that the fact that each weight has multiplicity 1, and the other facts about the representation space. So R is an irreducible representation of the Lie algebra of SU2, which we're calling SL2. We're labeling it by this alpha. And okay, so this is finite dimensional, this representation, the weights, for example, finite dimensional. And so we have, we use our knowledge of SU2 irreps and say that R is got to be some irrep for some highest weight, lambda, which is in the natural numbers, including 0. Set of 0 and all natural numbers. So in other words, SR is going to be from minus lambda plus 2 all the way up to lambda. And so what this means is that rho has to go between different integers. So rho is valued in the integers, as we know, but it goes between some positive number and some negative number. Where the numbers are integers. So n plus is bigger than or equal to 0, and n minus is less than or equal to 0, such that, okay, so minus lambda is when we've lowered n minus times with respect to alpha. And also plus lambda is when we've raised with respect to alpha n plus times. Well, I guess we'll have lowered it by minus n minus lambda times, strictly speaking. So we add these two equations. And we obtain an important constraint. That's 2 inner product between alpha and beta over inner product with alpha with itself is equal to minus n plus n minus. And this is an integer. And this is this equation is for all alpha and beta in the root set. This equation I'm calling 6.8. Okay, good. Now, I believe we labeled an equation 6.5b last lecture. Just check I did it properly. Oh, no, I didn't. Okay. I missed it. 6.5b is the second one here. So we've got 6.5a, b, and c, I guess. So 6.5b is this one between h alpha and e beta. Okay, and this is the thing, this factor here, oops, I'm going to call this now R alpha comma beta. Now, if you look at 6.8, we've got R alpha comma beta on the left-hand side, and this is equal to some integer, okay? So R alpha beta is an integer. So in our Carton Bile basis, going back to the original big HI elements of the Carton subalgebra, HI and E delta is delta I E delta. And so kappa ij, our killing form metric, so remember this is the trace of the adjoint of HI composed of the adjoint of HJ. So this is equal to the sum over all the roots in the root set of delta I, delta J. And to derive this, we basically need that, so remember that the adjoint HI of some vector in the Lie algebra Y is HI YCTC. So this is in terms of the basis matrices of the Lie algebra. So, okay, this is just summed over the basis matrices. So if I now I use the Carton Bile basis expansion for these TCs. So we have two terms. The first lot are over the elements of the Cartan subalgebra. So we can expand those HJ. And then we have plus sum over the roots in the root set of HI and say Y delta E delta. Okay, so of course the elements of the Cartan subalgebra, HI commutes with HJ, so that term goes away. And so we get E delta. And then of course you have to take, you have to substitute this into what's above, but you're going to get sum of delta I, delta J. Okay, so what we do is we take this equation star. So now I've got this thing, I can't get rid of it. Okay. So we multiply star, the equation star, by this factor kappa to the -1 jk, kappa to the -1 il, alpha k beta l. Okay. So the left and the right hand sides we multiply by this. And on the left hand side, we're going to, if you look at and see what the definition of, it was a boxed equation we had last lecture of the inner product between alpha and beta, we'll see that's what we get on the left. But let me write it out in full. Okay, and this thing on the left-hand side, once you've managed to raise and lower indices appropriately, is the inner product between alpha and beta in our space, and this is equal to sum over the roots in the root set of. Okay, so we get we've got one kappa ij which links delta and alpha, and one kappa to the -1 il which links beta and delta. So we get the inner product of alpha and delta, and the inner times the inner product of beta with delta, and this is equation 6.9. Now, I just want to substitute in for our we define this R alpha beta above. So I'm going to substitute that into this equation. And moving some factors around, we're going to get 2 over beta comma beta is 1 over R alpha comma beta. That's the sum delta in the root set of R alpha comma delta R beta comma delta. All right, now remember that we showed above that these R's are integers. So what this means is that on the right hand side, we've got some rational number because we've just got the ratio of 2 integers. So in particular, this is real because it's the ratio of 2 integers, but in fact, it's rational more precisely. So hence, right, well, we have that, what that means is that beta comma beta must be real. As well. And alpha comma beta is, if we just rearrange the definition for R alpha comma beta, so just from the definition of R, we have that alpha comma beta is this. So R is an integer, and any the inner product of any root with itself is a real number, and so alpha comma beta must also be real. As long as the roots are in the root set. So we're beginning to get towards our real geometry here. So remember, the dual of our Cartan subalgebra is the span over the complex numbers of our roots, all roots in the root set. So this is an assertion, and I'm going to prove this now. Let's suppose this isn't true. Let's suppose that these alphas don't span the dual space to the Cartan subalgebra. Then we'll prove a contradiction. So if that's the case, there must exist an element of this dual space with a 0 in a product. So some lambda in LH star with lambda comma alpha in a product is 0. So this left-hand side can be written kappa ij lambda I alpha j, or it can also be written, because this kappa basically behaves as a metric, we have kappa ij lambda with the index upstairs and alpha with the index upstairs as well. So we can write it either way. And so now if we define h with a lambda upstairs, this is lambda I hi, then well, we've got that this thing commutes with all of the hi's because we've just got commutators between the h's and themselves, and they're in the Carton subalgebra, so they all commute. This is 0 for all h in the Carton subalgebra. But now if we consider h lambda commutator with E alpha, if you look back to our Lie algebra in the Carton Bile basis, you'll see that this is equal to the inner product between lambda and alpha times E alpha. But we've just said that lambda comma alpha is 0 for all alpha. So this is 0 for all alpha in the root set. So in other words, this h lambda commutes with all possible elements of the Lie algebra. And that's because we expand these in terms of the Carton subalgebra and these E alphas, but all of the commutators are 0. But then this leads to a contradiction, because if I take some span over the complex numbers of all of these such h lambdas, this is a non-trivial invariant subalgebra. So this contradicts this fact that the Lie algebra is non-degenerate. So I've been implicitly taking simple Lie algebras. Okay, so what about defining a basis for this dual space? Well, we can find R. So remember, this is rank of the Lie algebra. R roots to act as a basis. For the dual space. Oops. So I take a couple of them. Well, it depends on the rank. So I take the rank number of alphas and a real subspace. So LH star real, this is the real subspace. So this is, of course, within the dual space, which is defined over the complex numbers. And this is just the span. Over the real numbers of the alpha I. Okay, so since the alpha I span the dual space, any root can be written as a sum over the over these basis, the basis. Any root beta in the root set can be written as beta is the sum I equals 1 to r of beta I alpha I. By definition of this, of what this subspace is. And so now beta I are complex in general, or at least at this point. Okay, now, so if you consider beta inner product with alpha j, and we know this inner product from our previous arguments has to be real. Well, this is sum between I equals 1 and r of beta I, alpha I, comma alpha j. And this is also real. And since the inner product is non-degenerate, in other words, it's not 0, we must have that beta I is real too. So this implies that actually our roots are in this real subspace of LH star. Okay, because we can just all the roots we can expand in terms of real numbers times these alpha i's for all beta in the root set. Now let's take a couple of elements of this real subspace. So let's let lambda and mu be in LH star real. And so again, we put lambda is defined to be lambda I alpha I, and mu is defined to be mu I alpha I. Okay, so this implies that the inner product between the two is lambda I mu j alpha I alpha j is real. Of course. And if I now consider the inner product of lambda with itself, well, this is the sum over all delta in the root set of lambda comma delta, lambda comma delta. All right, so this inner product of lambda with delta is a real number, and so this is the square of some real number, so of course it's greater than or equal to 0, and it's only equal to 0 if the lambda with delta is equal to 0 for all delta. So with the equality, if and only if lambda comma delta is 0 for all delta in the root set. In other words, lambda would have to be the 0 vector for that. So what this means is that this inner product is a Euclidean one. And the real form, also the real subspace of this dual space to the Carton subalgebra is isomorphic to R-dimensional Euclidean space. Okay, good. Now, since alpha comma alpha is bigger than or equal to 0 for all alpha in the root set, as in particular, so we can define the length of a root. So I should just say we're going to use familiar results in Euclidean space. So we can define the length of a root because we have this semi-definite inequality. So we define mod alpha is plus square root of alpha comma alpha. We can also define an angle between the two roots. Just as we do in ordinary Euclidean space. So alpha comma beta is the length of alpha times the length of beta times cos phi. And of course, our picture, which is well familiar to you since school, at least, is that we have this angle between alpha and beta. Okay, good. So now we have these numbers are alpha beta, which are integers. So if we consider the following, we can define our alpha beta now in terms of this cos phi. So r alpha comma beta. Remember, this is by definition, this is 2 alpha comma beta divided by the length of alpha squared. So this is twice beta cos phi over alpha, length of alpha, and it's an integer. So now if I consider r beta comma alpha, well, since the inner product is symmetric, we also get alpha comma beta on the top. But now we have the denominator of beta, the length of beta squared, which is twice alpha cos phi over beta, mod of beta. And this is an integer as well. And we multiply these two things. So if we multiply these two right-hand sides, we get an integer. And so what the multiple is 4 cos squared phi is an integer. So what this means is that cos phi is plus or minus root n over 2, where n is in the set 0, 1, 2, 3, 4. So when we're considering roots of Lie algebras, we're restricting the angles that are between them, between the roots. And the different possibilities are given by the following table. So when cos phi is equal to 0, when phi is equal to 0, cos phi is obviously equal to 1. So this is when we have n equals 4, for example. So phi is 0 and we have alpha is equal to beta. So that's kind of not an interesting case. Another solution is when phi is pi by 2. And this is when alpha and beta are perpendicular. Another solution is pi, where alpha is equal to minus beta. And we have the solutions pi by 6, pi by 4, and pi by 3. These all have alpha comma beta bigger than 0. And there are cases 5 pi by 6, 3 pi by 4, basically pi minus these ones, 2 pi by 3, where we get a negative inner product. So that's interesting. So we've learned something now about the relative angle between roots of Lie algebras. So let's now develop a useful concept, which is a subset of the roots called simple roots. So what we do is we choose some hyperplane in this dual space. And we can divide the root set into positive and negative roots, depending on which side of this hyperplane they're on. So I'll call the positive roots phi plus and negative roots. So this is a partition, negative roots phi minus. So we impose that the positive roots lie on one particular side of the hyperplane and the negative roots on the other. So let's give an example. Alpha 2. So this is sort of 3D example. Imagine that alpha 1 is going into the page, and perhaps we've got more alphas that we don't see, but I'm just going to plot the first 3. So now, typically, it's easiest if we put the hyperplane through the origin. So we have the positive side of the hyperplane and the negative side. Okay, good. So this is equivalent to putting phi is phi plus union with phi minus, such that for all roots alpha and beta, if alpha is in the positive roots, this implies that minus alpha is in the negative roots, and vice versa. And secondly, if we take two roots in the positive, two positive roots, sorry, I should say for all alpha beta in the positive roots. For all alpha and beta being positive roots, alpha plus beta is in the root set implies that alpha plus beta is in the positive root set. So the reason we've done this is because it allows us to define an ordering of points in this space. So if we take x1 and x2 in this dual space, since x1 is bigger than x2, if and only if x1 minus x2 is positive, bigger than 0. So we can define this ordering. So a simple root is a positive root which can't be written as the sum of two positive roots. Let me write that down. So this is definition. A simple root is, I'm going to write positive as plus v e. Positive root, which can't be written as the sum of two positive roots. And the set of simple roots is denoted phi suffix s. Now, I'm going to give you an example now. And I'm going to pull it out of the hat, but I'll just to show you what we mean. So roots of L SU3, the Lie algebra of SU3. So I'm going to give you a definition of hyperplane as well. So one common definition of the hyperplane, but it's by no means universal, is, so we have a positive root if the first non-zero coordinate reading from right to left, right-hand side to the left-hand side, is positive. Now I'm going to show you probably next lecture how to derive the following roots of SU3, but for now we'll just take them as given. And the rank of SU3 is 2, so we have the following roots. So if I look at the definition of this hyperplane, I find that the top 3 are positive roots. And we have the following. These are negative roots. Now, the simple roots are these two. And that's because this one, not simple, it's the sum of the other two positive roots. Now, as I said, we haven't derived these, but we will do soon. Okay, thanks. We'll go on to look at derive more properties of the roots and the simple roots next lecture.